Have you ever tried building, I don't know, a piece of furniture without the instructions? You might get it done, but it's probably going to be a wobbly, frustrating mess, right? Well, building software is exactly the same. A great idea? That's just the start. To turn that idea into solid, reliable software, you need a plan. You need a blueprint. And that blueprint is what we call software design. It's the absolutely crucial step that takes you from knowing what you want to build to knowing exactly how you're going to build it.
All right, so here's our game plan for this explainer. We're going to walk through software design like an architect laying out a building. First, we'll separate the big idea from the actual plan, the what versus the how. Then, we'll zoom in, going from the big picture view down to the nitty-gritty details. We'll explore what actually makes the design good, because not all plans are created equal. We'll get real about the challenges every designer faces, and finally, we'll see how a single blueprint has to speak to two totally different groups, the developers building it and the people actually using it. So let's get right to it and lay the foundation. Every single software project, and I mean every one, has to start with this fundamental split. You have got to clearly define what the system is supposed to do before you can even start thinking about how it's going to do it. Getting this wrong, well, that's pretty much the #1 reason projects go off the rails. And this slide right here, it perfectly captures that split. Over on the left, you've got the requirements. That's the what. Just think of it like a client's wish list, a checklist of everything the system has to do. Something like, the system needs to let a user upload a photo. It's a statement of need. Simple as that. But then on the right, you've got the design, and that is the how. This is the architect's plan that makes that wish list a reality. It answers all the tough questions. How do we store the photo? What format? How are we going to compress it? How does the upload feature talk to the rest of the system? See, the design breaks that big problem down into smaller, manageable chunks, creating a clear plan so a whole team of developers can get to work at the same time.
Okay, so once you have that plan, you realize pretty quickly that not all parts of the blueprint are drawn with the same detail. A good design is kind of like a camera. It lets you see the whole big picture, but then it lets you zoom all the way in to focus on the tiniest, most intricate details. And that's the difference between high-level and low-level design.
So this is the bird's eye view. We call it architectural design, or high level. It's like the main floor plan of a house. It shows you the major rooms, what we call the main modules, and the hallways that connect them. So for an app like, say, Instagram, the main modules might be a user profile service, a newsfeed service, and a messaging service. This design lays out exactly how they all talk to each other. And just like the foundation of a house, this part of the design is really hard to change once you've started building. Everything else depends on it. Now, let's zoom in. If the high-level design is the floor plan, the detailed or low-level design is the plan for what goes inside each and every room. This is where we get into the nitty-gritty. It describes the guts of each module, the specific algorithms you'll use, the way data is structured, how you'll handle errors, all with enough detail that a programmer can just take this plan and start writing code. It's the difference between saying, this is the kitchen, and specifying exactly where every single electrical outlet, pipe, and cabinet will go.
And this slide just lays it out perfectly, side by side. The architectural, high-level design on the left, that's your building blueprint. It's the overall structure, the main modules, and their connections. The detailed, low-level design on the right is more like a complex circuit diagram. It specifies every single connection inside a module so it's ready for implementation. You can't draw the wiring diagram until you know the shape of the room, right? Same idea here. You need both. You absolutely need both.
So we know we need a blueprint, but what makes one blueprint better than another? Well, a truly great design isn't just about making the software work. It has to achieve a whole bunch of different goals, often for very different groups of people. You can really break it down into goals for the user, goals for the developer, and goals for the project itself.
First, and you could argue most importantly, let's talk about the user. For them, a good design is one they don't even notice. It just works. It's user-friendly, it's intuitive, it's reliable so it doesn't crash when they're in the middle of something. It's robust, right? So if they accidentally type letters where a phone number should go, the app doesn't just break, it gives a helpful message. And it's fault-tolerant, meaning if their internet cuts out for a second, it saves their work. The user doesn't care about your elegant code, they care about a smooth, dependable experience.
Now let's flip the coin and look at the developers. These are the people who have to build and then live with this system, sometimes for years. For them, a good design is readable and easy to understand, so a new person can join the team and get up to speed fast. It's designed for reusability, so they can use components that are already built and tested instead of constantly reinventing the wheel. But the big one, the most important one of all, is that it has to be easy to change. Maintainability. Can someone who didn't write the code fix a bug or add a feature 6 months from now without wanting to pull their hair out?
That, right there, is the hallmark of a great design for developers.
And finally, there's the project or the business side of things. Here, the goals are all about resources, time, and money. A good design means rapid development, which helps the team hit their deadlines. It's cost-effective to build and to run. It delivers high performance, so you aren't overpaying for servers. And maybe it needs to be portable, so you can move it to a different system without a total rewrite. The true art of software design is this constant juggling act. You're always trying to balance these competing goals. Making the right trade-offs, well, that's everything.
Of course, designing software isn't some simple, linear process. It's messy. It is filled with these inherent challenges that make it one of the most complex things people do. But over the years, we've come up with some fundamental approaches to deal with these real-world problems. You can think of these as the 4 horsemen of software design. First, you've got complexity. Some problems are just naturally complex, but a lot of the time, we make them even more complicated with bad design. Second is conformity. Your shiny new software doesn't live in a bubble. It probably has to connect to some ancient system or follow some rigid industry standard. Third, changeability. The only thing you can be sure of in software is that things will change. A rigid design will just shatter under the pressure. And finally, invisibility. This is a weird one. Unlike a building, you can't see the structure of software. You can't walk by and see that 30% of the code is done. This makes it incredibly hard to see problems before they become catastrophes. So how do we fight back? Well, there are 2 classic strategies. You've got top-down design. That's where you start with the whole system and just keep breaking it down into smaller and smaller pieces until each piece is simple enough to actually build. Then there's bottom-up design, which is the total opposite. You start with existing, proven pieces, like an open-source library or something you've already built, and you figure out how to assemble them to create the bigger system. In the real world, the best designers use a mix of both. They'll sketch out the big picture top-down, but they're always looking for chances to use existing parts from the bottom up. Okay, this brings us to a really critical point. That final design document, our blueprint, isn't actually written for just one person. It has to speak clearly to 2 very different groups. The technical team who's going to build the thing, and the end users who are, going to live inside it. So let's look at the specs for the builders first. This part of the blueprint is the team's shared language. It's super technical. You'll have system models, like flowcharts, showing how information moves around. It'll define exactly how data is structured. It even gets into rules for things that sound tiny, like how to name variables. And that's not just being picky. Without those rules, you'd have one developer calling something customer_email and another calling it email address, and that just leads to confusion and bugs. These specs are the source of truth that keeps the whole engineering team on the same page. And now, for the other side of the coin, the specs for the user experience. This part of the design has nothing to do with algorithms. It is all about the human. It defines the standards for the user interface, the colors, the fonts, the size of the icons. It specifies the exact wording and tone of error messages. It even covers ergonomics, asking questions like, what's the most efficient order for fields on this form? What keyboard shortcuts do our power users need? This isn't just about making things look pretty. It's a whole discipline called UX design, and it's all about making the final product work for people. And all of this brings us back to the ultimate challenge. We create these incredibly detailed blueprints to build the software we need today. But we know for a fact that today's needs are going to change. The business will evolve, technology will leap forward, and users will want new things. So that leaves us with the fundamental question that really separates the good designers from the great ones. A design is a plan for the present, but it has to be a foundation for the future. So how do you design for a future you can't possibly predict? That question is at the very heart of great software engineering.